11. Can someone hear me?
Yes, yes, you're clear.
Yeah.
Okay.
Yes.
Okay,
Yeah,
great.
we can hear you.
Okay, I'm Jean-Baptiste Fankam. I'm a postdoc hosted by Professor Nosipo. So I will continue to chair this session. So now we have the presentation of Dr. Bertrand Sone. Bertrand, you have the floor.
Thank you very much, Dr. Fankam. The title of my presentation is ZnO via Hyphaene Thebaica fruit extracts. Hyphaene Thebaica is some plant from Egypt, called popularly known as Doom. So our work this work I'm presenting was actually done with a postdoc at CPUT about 2 years ago. And it was published in 2022, I think, 2022 rather. And the ZnO that I prepared using the plant extract was used to catalyze the ozonation of a dye known as Coralene rubine S2G. It's a dye popularly used in industry. So I'll be presenting work on the characterizing we did on the nanoparticles produced from that ZnO, from the extract, and as well the study we did on the catalytic effect and the explanations we gave behind that as far as ozonation was concerned. I'll skip that slide. So essentially, dyes known and are used for so many things in industry, as pigments and paper industry, printing, textile, and so on. Generally, dyes contain refractory organic molecules. They need to be that need to be broken down before you actually send or dispose of the effluent and the wastewater, the water that comes from the treatment. And usually, because these organic molecules are a little bit stubborn, you need to assist the breakdown of the organic molecules before you actually release them into the environment. Otherwise, then you contaminate surface and groundwater, and that is bad to humans and the environment. Methods that have been used to deal with effluent and contaminants in effluent and wastewater, filtration, coagulation, aerobic and anaerobic digestion, and so on. Chemical methods, the first 5 I've listed up there will deal with physical methods and biological methods. The ability to break down organic contaminants are not always the best. So chemical methods are usually brought into play, and you have chlorine, the use of chlorine, the use of hydrogen peroxide, the use of ozone, and what we generally call oxidation processes that involve the generation of radicals. And these radicals usually help to break down the organic molecules in the effluent into more environmentally friendly forms, such as carbon dioxide and water. So generally, sorry if I go back to my last slide, ozone has been used to treat effluent and has been shown quite effective, and yet limited in its ability sometimes to completely break down organic pollutants. So one of the things that has been done is to use metal oxides to assist or catalyze or assist that break of the refractory organic contaminants into things that are more environmentally friendly. And so, you see quite a lot of work that is in the literature that talks about the use of metal oxides. Now, what these metal oxides have been prepared with different, but at the time had been prepared with different methods. Study when we started the study, when I designed it, there was not much reported on using green zinc oxide prepared using plant extract. So we did this attempt. And so essentially, that's our doom. The reason for using the plant extract is that the plant extracts generally contain phytochemicals. And in the case of this plant, you have steroids, you have glycosides, flavonoids, and so on and so forth. And the presence of these phytochemicals produces, these phytochemicals have a chelating effect, or they surround the zinc oxide precursors or the metal ions, and they kind of limit growth. And because they limit growth, so size therefore is kind of limited. And the reason for using them, one of the reasons therefore for using them is that you want to be able to limit the growth of your nanoparticles so that they really, you effectively produce nanoparticles, yeah. So on the right-hand side there, you would see how we went about doing that. We basically take the extract, put salt there, and we heat it up at about 150, dry it after we've decanted the extract, it at high temperatures, and you have your zinc oxide powder. So that this is a picture to the right, top right there. Top right is a picture of the zinc oxide nanoparticles that we actually investigated, annealed at 400, 500, and 600 degrees. Yeah, in air. It was in nitrogen, I think. I would just need to check that. Yeah, I think it was air. So we characterize them using XRD, and usually, yeah, found out that with the you want to make sure you've produced zinc oxide. So you can see to your left-hand side there, that's our commercial zinc oxide at the bottom, and that's our zinc oxide at 400 at 500 degrees annealed at 600. And you would see that indeed the peaks correspond to that for hexagonal, for zinc oxide in the hexagonal phase. We did, we used the H.E.A equation to be able to calculate the crystallite size and then do comparison of them. And we found out that generally we had nanoparticles for all the green-synthesized zinc oxide nanoparticles, particles that were produced with sizes that were comparable to that of the zinc oxide 500 there, with the size close to that of zinc oxide commercial. And of course, you can see that the zinc oxide, the rest of the zinc oxide particles had sizes just slightly bigger than that of commercial zinc oxide. We did this, I think it was TEM, yeah. We did TEM, and we effectively wanted to just kind of look at the particles at a bigger scale, not at crystallite size, at grain size kind of. Yeah, and essentially what we gain after desonicating and subjecting them to the microscope electron beams, we were able to come up with the fact that, yeah, particle size is also within close to what we found with the light size, and we observe similar trends with zinc oxide commercial and zinc oxide 500 having almost similar particle sizes. And yeah, you can see the trend there in how the crystalline size variated with temperature, with increase in temperature. So if you look at the TEM and the XRD, you see that there's quite some correlation, which is expected, yeah, because crystalline size in XRD are just a small representation of what you actually find in the grains at 10, which you observe in 10, yeah. So we did FTIR, and if you look to your left there, you will just find out that was FTIR for zinc oxide commercial 400 at 500 and at 600. And essentially to the right of that, what I want you to take note of here is that to the right of this profile, FTIR profile, you find out that for zinc oxide, there's practically, there are no peaks present in the below 1,500. Whereas when you look at all the other green synthesized zinc oxide nanoparticles, you can effectively see peaks there, which can be attributed to the zinc bond for at 500 to 800 wave number. And then you find the other bonds there, which are the CH bending, CO stretching, CN stretching, all of which come from amines, phenolics, and so on. And essentially, this really just tells you that even with the samples that were annealed right up to 600 degrees centigrade, you actually find out that there is the presence of phenolics, of phytochemicals was still there. Definitely not in their form, but in terms of having been broken down, but somewhat still bound to the zinc oxide nanoparticles, or somewhat, embedded there. You would also discover that as we moved from zinc oxide commercial and we annealed at 300, you'll find out that the peak for zinc oxide, the peak for which at 3,500 wave number, which is synonymous to the presence of surface adsorbed water, was less prevalent and practically almost disappeared with the sample that was annealed at 600, meaning that, the water had effectively, any residual water in the system had been eliminated. So what this tells us essentially is that our green synthesized zinc oxide did contain residues, whereas organic residues, whereas our commercial zinc oxide did not have those organic residues, and that's because they were not prepared using phytochemicals. The industrial way for preparation is different from what we were trying to do. I think I forgot to say that one of the goals for doing green synthesis is that you want to produce your chemicals in a way that is more sustainable and simple and eco-friendly. So we therefore went on to investigate our synthesized zinc oxide nanoparticles as well as the commercial in terms of their band gaps. So we took reflectance measurements and we did a calculation on the band gap. And if you see here, I think this was using the Bertrand function. If you see here, this is your profile for zinc oxide in bulk form, which is at about 3.3 electron volts, sorry. And essentially all that had to do with all the green synthesized zinc oxide nanoparticles actually had their band gaps below that. And we attributed that to the presence of oxygen vacancies, which you can already see in the color of the green synthesized nanoparticles, zinc oxide nanoparticles. You can see in the color that they were somewhere around green oxygen, and that we do not think is just because of the phytochemicals. We think that's because of the oxygen vacancies that are there. Oxygen vacancies are known to reduce the band gaps. So we had that reduction in band gap there. Initially, what you see in the pink there was our zinc oxide, which stored initially at 3.14, stored for some time. Initially, when we prepared it, it had a band gap of 3.14 electron volts. But storing it over time, it became partially oxidized, and so its band gap increased. So when we ran ADX, we did, as we did the same, we ran ADX, we did a calculation on the oxygen zinc ratio, and we saw from it that the proportion of oxygen zinc ratio was lowest for that of zinc oxide. The zinc oxide prepared at annealed at 400, followed by that of zinc oxide annealed at 500, and that with the biggest or the lowest, the highest oxygen zinc ratio was that of commercial zinc. And if your substance, your material is highly substoichiometric, then it should have a very low oxygen to zinc ratio, and that is exactly what we found here. So it meant that of all our samples, the zinc oxide commercial, that was least substoichiometric, yeah. And the one that had the highest substoichiometry was that of zinc oxide 400, yeah, or the highest number of oxygen vacancies. Now that will become very important, as we will see in terms of the performance of the material in terms of the catalysis. So this represents a setup in which we did a scheme of the setup in which we carried out the ozonation. And essentially, you can see from here that's a sample before ozonation, and that's the water after ozonation. I'll jump on that. If there are questions to that, I'll come back to it. Yeah, so now we did, using the Lange-Hensherwood model, we did a plot of the concentration of the degradation over time of all the 4 zinc oxide samples. And we found out that our best performing catalyst was actually that of zinc oxide 500 and 400. Here you see in the blue there is our sample with no ozone, with no zinc oxide. And there you see our sample with zinc oxide 500 and zinc oxide 400. And you see a time difference of about 5 minutes. Now to this, the orange one there, peak of profile there, you see it's our sample prepared, in which zinc oxide commercial was used as the catalyst, and we see that the time difference was even way higher than that of the sample in which we used only ozone. And there are reasons we're going to explain that later. So essentially, we found out that generally all the zinc oxide particles prepared using green synthesis were performed better in terms of their catalytic effect. They're all down here when you compare them to the commercial zinc oxide. Now, we explain that one by the effect of turbidity. This one, though it was particularly small in size, it had about the lowest size in terms of particle size. We observed that there was quite some turbidity, but we do not think that is just turbidity alone that explains that. We think that the absence of oxygen vacancies and phytochemical residue in that commercial zinc oxide is what accounts for the very poor performance that we observed. Yeah, you would have thought that with maybe high surface area, this turned out to have the highest surface area, you should have improved performance, but that's not observed. We realized that even though it had improved performance, it had even though it had a high surface area, and even though, yeah, sure, thank you. Even though it had a high surface area, and even though it had a low, the smallest particle size, its performance in terms of degradation was very poor. And this, we think, is because of the presence of the lack of oxygen vacancies and the absence of phytochemical residue that has been shown to also help in catalysis, enhancing the catalytic effect on ozonation. Yeah, so this essentially, since my time is short, I'll not be able to go through this. But in this slide here, we show calculations on the kinetics of the ozonation process. And we see a first stage and a second stage. Usually the second stage is attributed to zinc oxide dissolution. for when you use a zinc oxide catalyst. But we found out that when we use the ozone, even without zinc oxide, it also showed a second. And we went on to give a reason as to why that second stage behavior is, and we believe that that's because as the reaction goes on, the pH of the sample reduces, and when the pH of the sample of the whole system reduces, there's a promotion in the formation of OH radicals. And while these OH radicals are increasing in their number, you actually have a reduction in the amount of the dye that is in the material. And when you do a proportionate, you do a concentration, when you compare their concentration, you would find out that that would tend to increase the kinetics as observed there. So you have this much faster kinetics, which is more a result of the high levels of ozone, the high levels of OH radical formation, and the reduced concentration in the dye at that particular moment. And so, yeah, that was what we discovered. So we said that it wasn't zinc oxide dissolution that was responsible for the second stage kinetics. Yeah. So we just show how the kinetics goes with the zinc oxide types, and we found out that it showed that the best performing catalysts were that of zinc oxide 400 and zinc oxide 500. And then we also found out that the rate kinetics varies, increases, and surface area increases, the surface area of your catalyst, except in the case of zinc oxide commercial, which even though it had a high surface area, because of the absence of oxygen vacancies and because of the absence of phytochemically derived organic residues that help in catalysis, produced a very poor performance in terms of rate kinetics. Rate kinetics is what you see in blue there. Yeah. And then we also found again that if you try to do a model of the grain size, increase in grain size, so you see the increase in grain size going there, and you compared it to the rate kinetics, again, you found out that generally you would see for first and second stage rate kinetics that there was an increase in the rate kinetics as the grain size increased. But again, the exception was seen with zinc oxide 500, that even though its size was really small, almost similar to that of zinc oxide commercial, it still produced the best performance in terms of rate kinetics. And that again is because of the high content in oxygen vacancies and the oxalic residue that is there. So that really promoted catalysis in that particular sample. Yeah, so in conclusion, what came out for us in the study was that we're able to show that oxygen vacancies and phytochemically derived organics in the green synthesized zinc oxide nanoparticles really make them a better alternative to commercially produced zinc oxide in terms of catalyzing ozonation of the dye, which was Coralene rubide. We also showed that instead of zinc oxide dissolution accounting for the exponential increase in the second stage kinetics, what happened is that there is a sharp drop in the Coralene rubide concentration with respect to the OH radicals, and this is what gives the impression or the effect, this is what gives us the faster second stage rate kinetics. We also were able to show that generally rate kinetics for the zinc oxide catalyzed, the ozonation catalyzed with green zinc oxide was proportional to the surface area, increase in surface area and increase in the grain size. Yeah. So thank you. So that was a paper we published in 2021, and yeah, was it 2021 or 2022? And the acknowledgements go to my colleagues at the time. Yeah, I'm now in UP. So thank you. Questions?